we went through Wein's displacement law, and there were some questions below. Here, the first node, the color. Did we discuss this? No, right? Okay. The color of a body which is hot enough to emit visible light depends on its temperature. So we have this idea, right? Because look, from this graph, we understood that when temperature increase, then the probability of shorter wavelength is high, right? When temperature increase, only the probability of shorter wavelength is high. That means it will slowly have more light in the visible region. Okay, so it should have sufficient temperature. If it has sufficient temperature only, it will emit visible light. And note number 2, at about 1200 Kelvin, visible wavelengths which are emitted lie predominantly at the red end. Okay, let's say at this temperature, the body looks red. And when we increase the temperature, when it is red, we call it as red hot. And when we increase the temperature, the color changes from red to white. That means it is actually becoming more yellow. Okay, it is becoming more yellow. And we call this temperature or this temperature as white hot. So white hot is hotter than red hot. Hope the idea is clear. And with that idea, when we look at our sun and at our stars, which one is more hotter? So the sun looks white hot, right? It looks for us like it's yellow in color. But the stars, they look blue in color. So stars blue color has a shorter wavelength, right? It has a shorter wavelength. Therefore, stars are much hotter than the sun. Okay, is the idea clear? And we have a few questions below. Did you all try this question? So here you can straight away use this equation because they are talking about the corresponding maximum intensity. So the value of the constant C was already given. And if you use the calculator, you can find this temperature. And similarly, here also the second question is also similar. And here we use the log. It is obvious that calculating this value using normal division is not easy. Therefore, we can use log. You know, if we take log, then log t is equal log this value minus log this value, right? So that is what it is written here. And the first thing, when we deal with log, it is always easy for us. If we write, we have to write these values in scientific notation. Okay, so this is also written in scientific notation first. Once you have written in scientific notation, now here you have a multiplication, right? You have a multiplication. So these multiplications can be written as additions. Log this plus log of this. So here we know that log 10 to the power minus 3 is equal to minus 3. So that is how we got this -3 in front. Use the log book to find this value. And here we have log 7. Yeah, log 7. And this -7 comes in front. Because we have a negative, it became +7. Okay. Then we simplified. And we use the log table to find the anti-log and get the value. Okay. Do you all have any problem with using the logbook? Or is it clear? Can you all do it? Then emissivity of surface. So this is a normal body and this is a black body. We know that black body can emit all the types of waves. It can emit all the types of waves. And its emissivity is E dash. Okay. But a normal body, can it emit all the wavelengths? No, right? Therefore, its emissivity is lesser, and let's take it as E. So, the emissivity of a body is a comparison between what this normal body emits with what a black body can emit. Okay, so here, emissivity of surface E indicates how well a surface radiates. That is obvious, right? So what we have to do is look at the definition properly. Both the definitions, emissivity and absorptivity, are slightly different. Okay. So, emissivity E is equal total radiant power per unit area. That means E, right? E dash over E, or the black body. Okay, so this is the equation. And if you look for absorptivity, the definition is slightly different. Because in absorptivity, we are not able to measure the power. Now, you cannot measure how much power this one absorbed, right? Because power is energy per second. So what we have to do is we have to look for a certain period of time. For some time, that means let's say for some number of seconds, we are comparing both the bodies. We are comparing this body with another body, I mean a black body. And in this given time, we are looking how much energy normal body absorbed versus black body absorbed. So the ratio between them is the absorptivity. Absorptivity A indicates how much of energy is absorbed from the total amount of radiant energy falling on it. So here, A is the total amount of radiant energy absorbed by a surface in given time. So this is important. Total amount of radiant energy falling on it during the same time. Oh, sorry. Here, it is not black body. Now, here, let's say E dash amount of energy is falling. For example, 100 joules. Let's say 100 joules of energy is falling on this body in a given time. Let's say in 10 seconds. But during that same 10 seconds, only 80 joules was absorbed. Okay, then here the absorptivity is 0.8. Is the idea clear? What I said previously was incorrect. So that is the difference between absorptivity and emissivity. In definition, there's a slight difference. In emissivity, we actually compare between a normal body and a black body. But when it comes to absorptivity, we are only looking how much we gave and how much it absorbed during the same time. Okay, clear with the definition. And when it comes to black body, emissivity and absorptivity is equal to 1. Okay, it is equal to 1. Modification of Stefan's law for non-black body. So we can obtain an equation for non-black body objects or a normal body. So we know that emissivity is E over E black body. So E is equal simple E times E black body. Now we can replace the equation that of black body. Okay, now here it's E. So power is E A sigma t to the power 4 into simple E. I hope you all can remember the E over here. This is not energy. This is power over area. Okay, from definition, it is power over area. So if you want to find the power, you have to just multiply by the area. So not, let's find the net emission. From this surface, we have an object with a thick wall. Let's say in this, the inner wall is going to have a different temperature. The outer wall is going to have a different temperature. So both of them are going to have different emissions. Now the inner wall, it has temperature T, therefore its rate of emission is sigma T to the power 4. And this one, this surface is also going to emit in the opposite direction or in any direction. Now, here, why did I use negative? The reason is when this emits, this is going to absorb, right? This is going to absorb a certain amount. And remaining only will pass through this wall. That is why we have negative. Okay, some of them is absorbed. So the net emission through this wall is sigma T to the power 4 minus T naught to the power 4. Higher temperature minus the lower temperature. Okay. So this is for black body. For practical body, we will have an E in front. Try this example also. Expression for intensity distribution of black body. So here, this solid line drawn with the pencil, that is the experimental data. That is the experimental data. And there was a theory, Wein's theory. His theory, it was only suitable for lower temperature. Sorry, smaller wavelength. But for larger wavelength, it's deviating. Look, it's deviating. And then we had Rayleigh-Jean's theory. His theory only suited for longer wavelength. When we had to draw the graph for shorter wavelength, it was not suitable. So both the theories, they were suitable only for a certain region, not the complete graph. So later, Max Planck, he introduced the concept of photons, that energy is quantized. Okay, he didn't give the name photons, but he said that energy is quantized. So quantized means that there is an equation like Q is equal to NE, where Q is the total amount, that is the physical quantity or the amount quantity, and E, this is the quantum. That means you cannot further divide this into a smaller amount. This is the smallest amount. And this n, it will be a whole number or a whole integer. So always this energy will be integer times this quantum. It cannot be 1.5, it cannot be 2.5, it can be 3 times or it can be 4 times. So this idea, using this idea, they explained this graph, and it perfectly suits with the experimental data. Okay, so that is only you have to know about this part, and I ask you all to copy the note up to this. So I hope whatever we discuss now is clear. Do you all have any doubt? Could you all note it completely? If not, leave some space. Taiba, how about you? Have you copied up to this? And do you have any doubts? You join in middle, right? Mm. Okay, right? Saja and Shahama, do you all have any doubt? Okay, so then we can start the next part, quantum theory of radiation. Quantum theory of radiation. So previously we discussed that uh, Max Planck came up with a new idea of radiation, that it is not continuous, but it's discrete. It is having small energy packets. You might have studied in chemistry when you started unit 1. So according to Planck, according to Planck, he says that energy is quantized. Energy is quantized. And the quantum is called photon. I remember photon was named by Einstein. He just said that energy is quantized. Okay. So according to him, radiation electromagnetic radiation is emitted or absorbed in discrete packets of energy. Packets of energy called photons. Therefore, energy is not continuous. Therefore, energy is not continuous. Third, the energy associated with a single photon. So this is important. With a single photon is given by E is equal to HF. So in this equation, this energy is not the continuous energy. This is the energy of a single photon. If we have n number of photon, then the energy is n times E. So here, given by E is equal to HF, E is equal to HF, and H is the Planck's constant. H is Planck's constant, which is equal to 6.602, right? I'll check the variable tail. And F is the frequency. E is the energy of a photon. E is the energy of a photon. So it's a 6.62 into 10 to the negative 34 joule second. Okay, not joule per second, it is joule second. Note number 4, the fourth one, the energy absorbed or emitted is always an integer multiple of HF. So according to that, delta E, that is the absorbed energy, is equal N times HF, where N is equal 1, 2, 3, and so on. And very importantly, the photons, although they are just like particles, these photons do not have mass. Photons have no mass, charge. But they have energy and momentum. but have energy and momentum. Okay, copy it up to this. Once you have copied, let me know. So this momentum here, you might think P is equal to mv. Therefore, it has to have certain mass and certain velocity. Then only we will have a momentum, just like that. But this momentum is not the momentum. It is not the equation that we use for classical physics. Okay, so it's completely different. So this is not the equation for the momentum of photon. Okay. Once you have copied, let me know. E is equal to hf, but we know that C is equal to f lambda. So we can obtain an equation for frequency. Look, here this is the energy of a photon, and this is the speed of a photon, because we know that's the speed of light. So C is equal, sorry, frequency f is equal C over lambda. So replace f with hc over lambda. Then we also have another equation for energy of a photon in terms of wavelength. Noted. Sajadan. Okay, so the next topic is photoelectric effect. Photoelectric effect. Now, don't write. First, let's understand what is this photoelectric effect. I'll completely explain this. After that, we can note. First, let's look at an example for the proof that there is some kind of phenomenon taking place when light UV radiation is focused onto a metal. So this is a piece of zinc metal, and here these are two metal foils. When we have negatively charged, when we negatively charge the zinc surface, when we negatively charge the zinc surface, then due to this negative charge, this foil is also negatively charged. Since this foil is negatively charged, they will be repelling each other. Okay, they will be repelling each other. Now, when we shine normal light, onto the surface of zinc, there is no change. There is no change. But if we shine UV light, if UV light is exposed, if the zinc material is exposed to this UV light, then we observe that these metal foils fall. These metal foils fall. So what is the idea you can get? If these metal foils fall, that means this is no more negatively charged. If this is not negatively charged, then there is no negative charge here. So there were negative charge. That means there were electrons. But when we shine UV light, these electrons somehow have escaped. Okay, these electrons somehow has escaped. So this phenomenon we call as the photoelectric effect. And this is a simple proof for the photoelectric effect. Okay, let's watch a video. We'll understand.
Do that using the method of charging by induction.
So they are charging first.
Now let me show you that again. Got a perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on. And it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
Okay, so did you get an idea about this effect? If it is visible light, nothing happens. And if it's UV light, there is something going on. Okay, it's releasing the electrons. So what's the reason? Now, when we compare the energy of a photon, the energy of a photon increases when the frequency increases. Okay, when the frequency increases. So the idea is simple. Now, a photon that has sufficient energy can remove an electron from the surface. So now let's say we have a photon that has more energy. Now I only need energy E dash to remove, but the energy initially E is greater than E dash. Then what will happen? Will an electron get removed? If the energy of a photon is greater than that of the required, will it get removed? Obviously, yes. If it is less, will it get removed? No. So in case of visible light, the energy of a single photon is not sufficient. Okay? It doesn't matter how much bright. It doesn't matter how much bright this light is. Brightness doesn't matter. Is that simple idea clear? Rahama and Taiba?